Welcome everyone. So this is our 111th live stream geometry. Today we are going to go through problems from the Thailand Team Selection Test. So we have 3 people here with us so far, and if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet on Sundays at 8 a.m. US Central Time. All right, so I'm going to share my screen. And hold on, give me just a moment. All right. So today, what's good is I built certain tools into GeoGebra. So we should be able to draw some of the diagrams faster. So I have triangle ABC. And we want to draw both the in circle and the X circle. So I have a tool for that that I built. So thanks, Abdul Heel, for mentioning this. Let's just go like this. Whoops, I forgot this part. Oh well. So I'll have to fix that with my tool. But it starts out drawing a lot for you, which is a good thing. So I might have to rename a couple things though, but that's okay. Okay, so we have a triangle ABC. Let's draw the circumcircle. So it's going to intersect this line at the midpoint of our BC, which is M. And the in circle is centered at I. So yeah, I got to rename it, which is BC at B. The X circle is centered at IA. It touches BC at E. And so lines MD and ME intersect omega at T and R. So those should be isogonal because D and E are like reflections about the midpoint of BC. So ME intersects it at R, and B intersects it at T. And looks like we have someone else. Hello, thanks for joining us. We're on our first problem. Just a heads up, your video's on, so I can turn it off if you'd like, or you can continue if you want. Okay. So MT and MR are isogonal. TR is parallel to BC. Let's see what else we can say. So yeah, it's a lot easier drawing the diagram with these tools. So RIA intersects the circle at S, and we want to show TI and S are collinear. This looks like a good problem. So why don't I call this G right here? Okay. Very interesting. All right. So R left, is this your first time on the session, or have I seen you here before?
No, it's the second time.
Okay. All right. Where are you from?
El Salvador.
El Salvador. Cool. Cool. All right. So this is weird. There's like 2 letters that show up. So I'll just hide that. So I'll just show L. Okay, so BD equals CE, that's well known. So MD and ME are like symmetric. So how would we show TI and S are linear? It looks like, okay, so it's actually a well-known fact that these are cyclic. So that's actually part of the Sharkey double configuration. I'm not sure what video that is on my channel. 100 something, but it's well known that if you take this circle, and it intersects the circle at T, then T, D, and M are collinear. I could prove that right now if you guys want another proof. It's not super long, but it takes a little work to prove that. So for now, I'm just gonna, let's see. S is the okay. So for those to be collinear, it's the same as saying, yeah, S is the antipode of T. In other words, TS is the diameter. Okay. So let's let O be the center of the circle. Another way of saying it is we want to show that T, O, and S are collinear. All right. No, I'm sorry. Not T, O, and S. A, O, and S are collinear. This feels a little familiar, actually. It's also the same as saying that angle ARIA is 90 degrees. We can show that, that would solve it. And then we wouldn't need point S. So that might be an easier way to do it. Yeah, we just want to show ARIA is 90 degrees, right? So if ATI is 90 degrees, I wonder if somehow we could use a similar argument to show ARIA is 90 degrees. It's probably like a similar argument, right? I'm not sure if it's the same argument, actually.
I think it should be the exact same thing because you can also draw in like the circle ARIA, and then it should be entirely symmetric.
A very similar argument. Okay, so the way that I show, that you show that angle, well, we know angle ATI is 90. Okay, so yeah, how do we show that R lies on that circle? Well, okay, we could define. Okay, basically we showed TD and M are collinear. Now we want to show RE and M are collinear. And the way we show TD and M are collinear is that we show TD bisects angle BTC. And we do that by the angle bisector theorem and some similar triangles. So I wonder if we can make the same argument here. We would want to show, see, we know TM bisect, we wanted to show here that TD bisects angle BTC. Here we want to show that RE bisects angle BRC. And I wonder if, so what we could do is we could let R prime be the intersection of those circles, and then we want to use the angle bisector theorem to show that R prime B over R prime C is BE over CE, which is BL over CG, and R prime CG is similar to R prime BL, so that proves that, right? That's the proof, I think, right? So yeah, that solves it. All right. So, I'm gonna like rewrite the proof of the whole Sharky Devil stuff. But yeah, once you know that concept, it's not that hard of a problem, really. So let AJ, I'll just say label the points as shown. And let AJIK intersect ABC at P prime. And let ALIAG intersect ABC at R prime. And first I'm going to show T prime D and M are collinear, then I'm going to show that R prime S and IA are collinear. And that will solve the problem. I'm sorry, R prime E and M are collinear. So we could still draw that segment if we want. Yes. So by spiral similarity, T prime JB is similar to T prime KC. Similarity. T prime JB is similar to T prime KC. And that means that T prime B over T prime C equals should be BJ over CK, which is equal to BD over DC. So that means that T prime D bisects B T prime C. By the angle bisector theorem. And that means that T prime D and M are collinear, which means that T prime equals T. Looks like Chuan either had to pop off or maybe his connection went down. Usually his connection goes down, so we'll see. Okay. And then we can make the same argument to show that R prime equals R, because we can first, spiral similarity shows that R prime CG is similar to R prime BL. R prime BL is similar to R prime CG. And that means that R prime B over R prime C is equal to BL over CG, which is equal to BE over CE. So by the angle bisector theorem, R prime E bisects angle B R prime C. Bisector theorem. And that implies that R prime, E, and M are collinear. Which means that R prime equals R. And thus, angle AR prime, so we want to show TI and S are collinear. So angle ATI is equal to 90. So wait a sec. Okay, yeah, it's just that if we know both of these are 90, then that pretty much solves the problem. So first of all, we have angle AR prime S. We know, or angle ARS equals 90. I'll say this is angle ARIA equal 90, implies that S is the antipode A, and that means that T, I, and S are collinear. Oops, I'm getting off this here. And that since angle ATI equals 90. All right, let's move on to the next one. So yeah, we solved this pretty fast. Yeah, Thailand is usually not that easy, but we just knew these tricks and it made things a lot easier. All right, so this one looks kind of interesting. We have two circles intersecting at points A and B. Maybe I'll just do it like this. And then we have a line through A intersects the circles at C and E. Okay. Let's see, C and E, and G is between A and E. So I guess there's a lot of flexibility in this kind of configuration. This is G, and now we are going to draw a line through B, and this should be D, and this should be F. So you can choose all these points however we want. There's a lot of flexibility. CH intersects FG at I. Okay, so let's make this easier to see. How do we make CH? We want kind of more, just we could shrink it a little bit. CH intersects FG at I, and DG intersects EH. Okay, so DG intersecting EH doesn't look so bad, but that's K. And so DG should intersect the first circle at L. And then for the other way, CH and FG. It's almost just barely off the screen. So let's move. There we go. That's better. Okay. These will intersect at L. Actually, I had a tool to do this, so you don't have to keep hiding stuff. But oh well. So DG intersects this at L. This should be J. So yeah, next time I'll use the tool, but I created a tool where you don't have to keep hiding all the lines things like that. EH and FG. We want to see. Okay, so really I should have drawn the whole line. So where do these intersect the other circle? EH and FG. They intersected at M and N. So this should be M, and this should be N. And what are they saying is cyclic? What is I? Wait, CH and FG intersect. Oh, this should be I. It intersects the circle at J. Okay, so that's I, that's J. So I wonder if this is just an angle chase, or if it's harder than that. So yeah, maybe it's really easy, maybe it's not. I would have to think about it a little bit more. But it seems like the problem's so flexible that I would be surprised if it's something really that deep. All right. So let's hide this. Whoops. And hide this. We're saying these are all cyclic. It's a lot of points. One second, I'll be right back. All right, I'm back. Thanks for waiting. And looks like Chuan has just rejoined. Hey, Chuan, thanks. Think about this. So J. So J, L, and N. Okay, actually J changes when I move this, but L and N stay fixed.
I believe this is just true by Cayley Bacharach, but I'm not exactly sure about like the conditions for degree 4.
Oh, really? That's advanced. Wow, Cayley
But I think it
Bacharach.
just works.
Really?
Yeah. So what the theorem says is, in this case, degree 4, you have two curves of degree 4 that intersect in 16 points, and then another one that goes through 13 of those. Then it also goes through the last 3.
Oh,
And
okay.
in this case, we have the first curve is like uh the small circle on the left.
Hmm.
Um, so that's 6 points. Then the line NGFI
Hmm.
and the line MHEK. So this is like degree 2 plus 1 plus 1, so 4. And we have this 14 points we see plus 2 circle points, which is 16. And then
Okay,
the same thing.
so this is 6, or this is degree 4, and then these two together are degree 4.
No, the circle on the left is degree 2.
Okay.
The one of the both of the lines are degree 1, so their
Okay.
union is degree 4. Like if you write down the equation that like has to be, or the polynomial that has to be 0 for a point to lie on on any of those,
Yeah.
um, to get the union, you multiply, so the degrees add.
Okay.
So so this is degree 4. This is the first curve, and then the second one is the other circle and the other 2 lines that each have 4 points on them.
Okay. This and these two.
Exactly.
Okay.
And now for the third curve, we have the line like CAGE and DBHF. And then the conic through any 5 of the 6 points we want to show lie on the circle. And now by Cayley Bacharach, we know that the other 3 points, which is first of all the 6th point out of these like KNLJMI,
Hmm.
and also the 2 circle points, they also lie on that conic. So we have these 8 points on a conic. So KNLJMI and 2 imaginary points, like um
They're just
and
imaginary.
yeah, they lie on every circle, which is cool because that's exactly what we need. So we know that these 6 points we want, they lie on a circle, and also they lie on a conic, and that conic also has the circle points, so it is a circle, and we're done.
The conic. Wait. So how do we know that conic is a circle? Is it because those
Uh,
imaginary points are on it?
exactly. Yeah.
Hmm. Wow. Okay. I'm gonna write that up, and then could we also try to find a synthetic solution? I think it's really cool that you can use stuff that advanced for this. Okay. So consider. Okay. So first of all, we have this circle and these 2 segments, and that's degree 4.
Yeah. Yeah.
So consider the following conics. So we have this circle ACPB, and then union. Actually, is cup, yeah, ACDB, and then union NI, union MK.
Yeah, I think so.
Okay.
Yeah.
That's first. And then the second is,
Oh wait, no, NI and MK is the other line.
oh, sorry, NI and MK. And then we have ABEF, and these, was it, sorry, so then we have the big circle and these 2 segments, so DK and CI.
Yeah.
So ABFE, ABFE, dk and ci. And then the third one, you said just these two lines, CE and DF.
The third one is yeah, the two lines, and then the third one is kind of we say that we take these two lines and then we take a conic through, say, KNLJM, so 5 out of the 6 points.
Okay.
And then we know that the other 3 also lie on that conic.
So okay, so CE intersect DF is the third conic, and then is that like a fourth conic, or that is part of the third conic?
It's part of the third one.
Okay.
And it's wait, it's a quartic, the third quartic.
Okay, so that's a quartic. That's not a conic, basically.
Yeah.
Okay, so CE, DF, and okay, so this is degree 4, and this is also degree 4, and so also consider the quartic. So CE, DF, and like KN, JL, MI.
Yeah, like through 5 of those.
Okay.
Because we don't know yet that like all 6 of those lie on a conic. That's part of what we want to prove.
Okay.
So actually, maybe I misspoke earlier. Like the first 2 are also not conics; they are also quartics or curves or whatever.
Yeah. All right.
Okay, and
sorry, go ahead.
now by Cayley Bacharach, we know that point I and the 2 circle points. I don't know. Maybe I think some people call them like alpha and alpha prime or whatever. It doesn't really matter. But notice that these also lie on the first 2 conics, and we have these 14 other points. So we have 2 conics that intersect in 16 sorry, two quartics that intersect in 16 points, and now we have 1 through 13 of those. So it also goes through the other 3.
Okay. Imaginary circle points. The imaginary circle points, alpha 1 and alpha 2, they like lie in all the circles?
Yeah.
2 lie on all the circles. By the Cayley Bacharach theorem, I must also lie on the last quartic. So what does the Cayley Bacharach theorem state?
If we have, so this works for like curves degree 3 or higher. In this case, we use degree 4. So we have 2 curves of degree 4 that intersect in 16 points. And now any other curve of degree, so these 16 points also need to be in like sufficiently general, like we can't have 5 on a line or
There's non-degenerate conditions.
Yeah.
Yeah.
But this should definitely satisfy it. So these 16 points, they intersect in 16 points. And now we have another quartic that goes through 13 of these points. Then we also know it goes through the last 3.
Okay. So the Cayley Bacharach theorem says if 2 quartics intersect in 16 points and another quartic passes through 13, then it also passes through the other three. So since the last quartic also passes through alpha 1 and alpha 2, I must lie on K, L, J, and M. Alpha 1 and alpha 2. I lies on K, L, J, and M, and that has to be a circle. I, K, L, J, and M must be a circle. Interesting. Okay, so we're saying that this quartic here passes through 13 of the 16. So CE, DF. So how do we know this quartic passes through the two circle points? Well, because it has to pass through the other three, but we're saying it passes through 13 of the intersection points. Okay, so we know these. Sorry, go ahead.
There's only 9 points there. Like you only wrote down 9 points, but it also goes to A, G, B, and H.
Okay.
Like line CE is just 4 points, but I mean, it looks like it's only 9 points when you write it down like that.
Yeah.
Because like line CE, but there's 2 more points on that line.
Okay. So we have let's look at these two. If we look at all the points that line both, so it's A, B, C, D. Do E and F line both?
Yeah, it's every point in the diagram.
Okay.
And 2 circle points.
Interesting. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Wait. So I get 14. Oh, but we left out I. Okay. This is a really interesting proof. Wow. I would never.
It's a really cool theorem.
Yeah. So yeah, if we're gonna do it synthetically, like we could try to show angle LKM is angle. Yeah, that's almost certainly the easiest way to do it if you know the proof of it. Yeah, otherwise maybe it's not that easy. Let's see. You think they came up with this problem by using this?
They might have. I don't know that like every so often there is a problem. Like there was like I think in last year's EGMA or something. You can never be sure, but like sometimes it really looks like they just tried to find an interesting Cayley Bacharach application.
That's fine. So maybe we could show angle DLJ equals angle LNI. That seems like it might be a good way to start. So angle LNI. Yeah, I don't know how you would figure that out though. Or LKI. So we could try to show angle DLJ is. We could try to show DLJ is JIK. That seems like it might be. But then JIK is kind of hard to figure out. DLJ, we know that's DAB. And DAB, yeah, we don't know too much about DAB.
One interesting thing is that EF is parallel to CD, just by Rime's theorem.
That's a good point. EF is
That
parallel.
could help with like angle chase.
Yeah. I'll just fix this typo.
And it appears that KI is also parallel to that, but I don't know why that would be true.
Interesting. Okay. Maybe we could use a ratio somehow. I don't know if it would help to draw this point, maybe show something with ratios. Well, actually, so I think if this were cyclic, it would follow that KI would be parallel because
Yeah.
yeah.
Maybe that is like a step one could do. Just
Yeah.
like to show that LJIK is a circle through this like those parallel lines, and then maybe find something else for the other points.
Yeah. Okay. So what kind of ratios can we use? Maybe Menelaus somehow. Sorry, I'll be right back again. All right, I am back. So DDI, the Desargues involution theorem and Cayley Bacharach, those are like two super powerful theorems. Yeah. I don't even really, so I guess a quartic, it's some kind of like polynomial equation with degree 4.
Yeah. Like if you write down like the equation for a line, it's like a homogeneous polynomial in degree 1, and
Yeah.
like the zeros of that would be the points on the line. And then
So
for
like,
every
so like, this might be like a quartic, for example. I don't know.
yeah. And to be able to work with
It can have lower degree terms though, right?
yeah, like normally you'd write it in like homogeneous coordinates. So like you'd have a third coordinate z that
Okay.
is like basically it's 1 whenever you have a normal point, and then you can um that way you can like define points at infinity in
Okay.
like a sensible way that you can also do calculations with it.
You're like projectivizing it so that you can deal with points at infinity instead of
yeah.
just, that makes sense.
And we actually need to do this for this problem because the circle points are points at infinity.
Yeah.
And like the reason they exist, or like one way you can show that they exist and that they are actually on every circle, is if you write down the equation for a circle, you don't have a term of like
So it's like this kind of.
yeah, you have like for a general conic, you would have terms of like something times x squared, y squared, z squared, and then also xy, yz, and xz. But for circles, you don't have the xy term. So whenever you plug in the coordinates of the circle points are like 1 I0 and 1 negative I0. And if you plug that in, you just get like you just get 0. So that's one way to show that they exist. Or that they lie on every circle rather. So and now if you just like write down an equation like that of degree 4, that's a quartic. That's what we call a quartic.
All right. But yeah, Chuan, I think it's very rare that yeah, you would use something like I guess maybe it pops up more and more that something this advanced could be used in a competition, but yeah, I think it's not that often. All right. So I've seen other people mention it before though. That's how I knew about it in the first place. All right. And yeah, I think I don't know how much you know about this, but like with elliptic curves, there's like a group operation where if you take any two, you can combine it to make a third. And like in order to prove that that's associative, I think you use the Cayley Bacharach theorem, or that's one way to prove it. Yeah, that's pretty advanced though. But yeah. Yeah, I've only seen it a few times ever before, so you're not that different from me. Yeah. All right. But yeah, I know the group operation on elliptic curves is like something really important, and the proof that it even is a group uses this, so this must be important then. All right.
I've just sent like a PDF to the chat. You can join, you can look at it if you want to. It's from a really cool book by like Adam Grouchers, I think.
Okay. Interesting. Yeah, I'll read through it after the session. All right. Let's see what time it is. It is 9:49. We could try to find a synthetic proof for a couple more minutes, and then I'll move on to the next problem. Okay. So how should we show that Ki is parallel to CD and EF? Should we draw this point? And maybe use Menelaus somehow? I don't know. So yeah, I mean, to show, so we wouldn't need points M and N to show that idea. What happens when we move H? So we move H. K. Let's see, E and F are fixed. It's just changing where K and I are. So we're saying as we move H, KI remains parallel. So that's kind of interesting. Why would that be? So yeah, we could fix G and move H. So this line stays fixed, line BG. Maybe it feels like it's just like projective geometry or something. So we're projecting K, E, H, and something through I onto C, E.
Oh, I think I can prove that they're parallel.
Okay.
So it is Pappus theorem on the points. I need to get the ordering right. C, G, E, and okay, D, H, F in some order. I can.
Yeah. So like,
And yeah, we don't actually need those lines.
okay.
Oh yeah, okay. So D corresponds to E, then C to F, and H to G. So this is like the order: C, G, E, F, H, D, and that means that the intersection of DG and HF, which is K, the intersection of CH and GF, which is I, and the intersection of CD and EF, which is just the infinite point at CD, they are collinear. So
Okay.
KI is also parallel.
All right. So yeah, it's just Pappus to prove that these are parallel. And yeah, I was gonna say it has to be something simple because yeah, you could hide so much of this diagram and still get the result is true. Okay. So by Pappus, that's parallel, and so we know from there that LJIK is cyclic, right? Because DLJ is DCJ is DCI is JIK. So we know that JLKI is cyclic, and now we have to show that M and N lies on that. All right. This figure almost looks symmetric, so I'll try to make it look a little less. Almost looks like DCEF is an isosceles trapezoid. So a quartic has degree 4 and a conic is degree 2. So that's the difference. For point N, you could try to show angle NIJ. So, I mean, if we show N lies on it, then by the same argument, M would lie on it, right? So we want to show angle NIJ. NIJ is 180 minus NLJ or something like that. So NIJ is GIJ. Like maybe it almost feels a little like the radical axis theorem.
Sorry, which theorem?
The radical axis theorem.
Oh,
Let's see if there's
yeah, I thought about that, but like that only gives you that these like 4 points lie on a circle, right? Like if you were to show NM, LJ, and BA concur, that just gives you like NM, LJ cyclic, but I don't see how we would like get that it's the same circle.
Yeah. No, I see what you're saying. So yeah, we know angle NIK. Same as angle GFE. So we want to show GFE is NLK. So yeah. Sorry, go ahead.
Sorry. One interesting thing about these radical axes is that GH also goes through that point.
GH.
Yeah. So GH, MN, JL, and AB all concur. And I think I'm not sure. I definitely use like the problem is true for one of those. And probably for both of. Oh no, just for one. And
that these concur.
yeah. So if we take out MN, that is just Pascal's theorem on BC. Oh God, the ordering is it's on some combination of the 6 points on the left circle, right? A, C, D, E, B, J, L.
So by the radical axis theorem, we know that we know that these three concur, right? Right, just on the three circles.
Yeah, like that uses that the problem is true, but yeah.
That uses that as true. Yeah, I see what you're saying. And then, so we don't know that yet. But then for this one, you think we can use Pascal's? Possibly?
Yeah. G is the intersection of CA and DL. H is the intersection of CJ and DB, and then we're left with like AB and LJ. So they're all collinear.
Okay. So if we can show that M, N, and O are collinear, then that would show that J, L, and M is cyclic. But that we still wouldn't know yet that M and N lie on the same circle, basically. Although it might not be that hard once we've shown that. But okay, so this we know. So I'll just make these segments. This we know by Pascal's theorem. And so this means that O has the same power with respect to this circle and this circle. But we don't yet know that that's this circle. Oh, we do. So O has the same power with respect to this, and the big plate. Oh, but we don't know. Okay, so we don't know the circle passes through M and N, but we know it passes through J, I, K, and L, and we know that it would have the same power with respect to these three. So basically we could let, I'm trying to think about this. Yeah, we just don't know that M and N are the intersection points. But what if we instead define M and N to be the intersection points? Or we could call them M prime and N prime. And so like I could hide these two, and we could define M prime and M prime to be or they intersect. And then we could try to show then we know that this is like this, and then we want to then we just need to show M prime, H, and K are collinear. That's one way to do it, I guess. I don't know if that's easier or harder, but
it seems really weird to do, like to
define
prove that, because once you redefine M prime and N prime, you can't distinguish them anymore. They're just like the two intersections of two circles. And now you want to show that one of them lies on one line and the other lies on another. That just seems like,
yeah, I see what you're saying.
that seems like the first natural step you would do is to like redefine them back to where they were before.
Yeah. Okay. So maybe it might be easier to like hide this circle. But we know that we're using the fact that that's cyclic. Yeah, I'm gonna hide that circle just for now. Let's see. So that circle's omega 2. Oh, no, really? No, I don't want to hide that circle. Maybe just hide this circle. Oops. Let's see. So once we've shown that I and JKIL, yeah, even if we show O, N, and M are collinear, I don't think that would solve the problem all the way. It might be a step, right?
Yeah, we would still need to find like some way to show that these are the same circle.
Yeah.
But I can't think of any like good way to do that.
Maybe the power ratio lemma, because we would have three circles all passing through L and J, right? And so actually, would that be three circles? L, J, E. Oh no, that would just be two circles, I think, right?
No, we would still have three circles. Like the one through C and D, and then like the two circles we want to show are the same.
And the two we want to show are the same.
But yeah, I don't know.
Well, let's see. So if we knew these were collinear, would that make any kind of angle chase easier? All right, let's think about this for like 5 more minutes. Let's see if there's another special point on this circle. Yeah, I wonder if there's anything like that concurs somehow. Yeah, let's assume for now that these were collinear. Can we say anything else?
Wait, I just found two new circles.
Oh, what?
Yeah, it's wait, I have like two things mixed up. ALGN and BJHM.
For cyclic?
Yeah.
Okay.
At the moment, just by like looking at the algebra, but I'm sure that like there should be a way to prove that.
Yeah. So angle JHM, it's half the sum of these two arcs, and angle JBM. Yeah, we don't know too much about JBM. But JBH and JMH, we probably know. Yeah, that's probably just an angle chase because yeah, angle JBH is angle DCH, and angle JMH is JIH. So that, but we're assuming that M lies on this circle. That's the thing. So yeah, if we can show JBMH is cyclic, I think that would solve this. Okay, let's remove point O for now. Because I'm not sure. Yeah, once we show JBMH is cyclic, I think that would solve the problem. That would mean that JMIK is cyclic.
Why is that equivalent?
Well, okay, so we know that JLIK is cyclic, right?
Yeah.
And then if we show that this is cyclic, then that would mean angle JMK equals JMH equals JBH equals CDCI, which is angle CIK, which is JIK. So we'd have angle JMK as JIK, and so JMIK
Okay.
would be cyclic, and that would solve the problem.
Okay. That's
Yeah.
cool.
So yeah, it's once we show that cyclic, it solves it. And maybe we could do that by showing angle BMH is BJC. And BMH is BME. Wait, is that trivial? I think this might be trivial. So BMH is BME, which is BFE. Which is 180 minus BDC, which is BJC. So I think that solves it. Because then we know that this is cyclic. Yeah.
Oh yeah, nice.
Okay. So I'll say proof 1. And then we have proof 2. So proof 2 by Pascal's theorem, or Pappus's theorem. So CH intersect GF. And then DG intersect CH intersect GF DG intersect DH equals K. And CD intersect EF. We'll just call that CD infinity. Are collinear. So that means that IJ or IK is parallel to CD. And that implies that IKJL is cyclic by Rhines. Then I'm going to show that M lies on that circle. So we have angle BMH equals BFE. So BMH is angle, BME is angle, BFE is 180 minus BDC, which is BJH. BFE is 180 minus BDC. Which is BJC. So that means that BMHJ is cyclic. And once we know that, then we have angle JME is JMH is JBH, or angle JMK equals angle JMH, which is JBH. Which is angle DCJ, which is angle JIK. And that means that JIMK is cyclic. Similarly, JINK is cyclic. And that implies that IJK element is cyclic. All right, so let's move on to the next one. So we have two solutions to this problem. That is not bad. I should write proof 2 so people don't get confused. Proof 2. All right. Let's check out the next problem. It is possibly easier, so we'll see. We have a triangle with circumcircle omega, and B is on AB. Okay, so I think we have a mixed linear incircle, I think. So I can use my tool for that. Give me just a moment. Oh, maybe it's not as easy as I think. So I don't think it is mixed linear incircles. So we have circle tangent to DB, because D is a point on AB. So, oh, but it's also tangent to DC. Okay, so we have a curvilinear incircle, not a mixed linear. I should know more about curvilinear incircles. I forgot how to draw them. So, is the point of tangent?
If you draw the angle bisector of BDC, we know that like the line connecting the points of tangency is perpendicular to that, and also it goes through the incenter of ABC. So we can just
ABC?
ABC, yes. So we can just drop the perpendicular from I to this angled bisector, and then we have.
Okay. All right. So I'll drop a perpendicular. Oh, so does it pass through these? Are these 2 points the points of tangency with BDC?
Yeah.
Okay. So then you can just do this and this.
Oh. Wait, what does externally mean in this context? Does it mean that like
Oh, you're right.
like it's not super clear, is it? Like does it mean that this circle gamma um intersects like is on the outside of the circumcircle, or does it mean that it
I think it does. I
like,
think they probably mean that. So DB, DC, and I think they might mean the mixed linear X circle. Yeah, or the curvilinear X circle. I don't know if I've ever drawn a curvilinear X circle. Yeah. We could well, let's see let's first see if we did assume this. I'm just curious. So the external angle bisector of ABC. So we could do it like this. Intersects MN. So how do we get this point closer? Yeah, it's kind of hard to draw. Let's see if I draw. Well, maybe I need to draw a taller triangle, and then maybe it would be easier. No. Let's see. So if this was X, does AX bisect angle? Wait, the external. Oh, of ABC, not BAC. Okay, so I drew the wrong external bisector. So then this would be like X. And okay, then it's not really true that AX bisects BC. So we really need like a curvilinear X circle. I don't know if you know a way to draw that. I'm not sure how to.
Yeah, I just figured it out. You just do the same thing with the excenter instead of the instead. No, wait. Oh yeah, no. And it just works out.
With the X
Like
circle. Okay.
yeah. You can do the same construction. You can even leave like the construction you already have and then like redefine I to be the excenter. It needs like a little bit of work, but it works out.
All right. Okay. Let's do that. There's point G. So, oh, it already gives me point G actually. So I don't really need to, I just need to draw in BG and make it a smaller diagram. Oh no, it doesn't actually draw point G for me. I thought it did. Okay. So I'll draw in point G. Or now it's calling it pen. Oh well. And I take the perpendicular from this point to to this line. Wait, I forgot what it did. So
Like the parallel to the line you just but like the perpendicular to line D or the bisector of BDC.
okay. Okay. So perpendicular to that. And I try to see where it's going to meet these two lines, AN and AF.
Yeah.
Okay.
Or no, AN and DC, because we want it to be tangent to DC, not
That's
to
right.
AC.
All right. Okay. These would be the points of tangency. And so I want to draw a circle tangent at O and E, and then tangent to BC, right? Or no, tangent to this circle, right?
Yeah.
And is the center of it the intersection of the angle bisector? So
Yeah, it works in exactly the same way as before.
okay,
Oh, no, the other angle bisector. It's still the bisector of at D.
at D. Okay. Whoa. Sorry. Oh, just that whole line. Okay. So I already drew the line, so I just need to go like this. And this would be the center of the mixed linear X circle. Nice. That's cool. All right. So I can hide a couple things here. To make it easier to see. Well, actually, I'll just make that a segment instead of a. All right. So we have this circle. Let me make the points like they are in the problem statement. I'll keep the end circle just for the heck of it. But I don't really need. Yeah, I'll just leave them. So why not? Let me rename stuff. So it's tangent to BB at M. And it's tangent to BC at N. And now we draw that external angle bisector. Maybe I already drew it. I probably did. Oh, I guess not. Okay. So that's the, oh, it's just BIA. Yeah. And we want to see where it intersects MN. So.
And like, just like in the first problem, we have something that's completely symmetric with like the in center and the X center. Like we had the lemma that, or we even used this like to construct points M and N, right?
Yeah. So this
M and
I think X is just IA, right? X
yeah.
equals IA, right? Yeah, so it's just like the first problem. It's how do I rename? It keeps. I want to get rid of M1. Let's see. There we go. So it's kind of like the way you constructed it assumes kind of the problem's true, right?
Yeah.
Because yeah, if it's true that you construct it the way you mentioned, then it's kind of obvious that x equals IA.
This is like known for the curvilinear in circle.
Yeah.
So I also didn't know that about the like X circle, but it's like generally if it's true for the in circle, it's probably true for the X circle. Much like swapping some interior and exterior bisectors. So like I don't know the proof of that for the in circle or the curvilinear in circle. So, but like if you
Yeah.
knew this, if you knew the proof, it would probably be a trivial problem.
Yeah. All right, we can move on to another problem, but yeah, maybe in the end, if we get through the other ones, then we could try to prove it. I think I've seen the proof before. I think it's somewhat similar to the proof for the mixed linear in circles. All the theorems involving that. But yeah,
Yeah, that makes sense.
let's try this problem. So we have a quadrilateral. So the projections of M onto the four sides lie on a circle with center O. So I'm going to first draw the circle, this circle with the projections, and then I'm going to draw ABCD. So, oh no, first I'm going to draw